Automobile loans, mortgages, investments, certificate deposits, savings accounts, and IRAs are all examples of important financial concerns for which we use mathematical formulas to calculate the value. Hi, my name is Tom Atwater, and in today's lesson, we'll be looking at the mathematics of finance. So let's start off by looking at a discussion or a table in which we're going to discuss compound interest. Here's the table. We have time in years in the left-hand column and that the amount of the account in the right-hand column. Now suppose we take a principal amount of P dollars and we invest it in an account bearing an interest rate of R, and if we express R in decimal form, then we calculate that interest at the end of each year. If A sub n represents the total amount in the account at the end of n years, then the value of the investment follows the growth pattern that you see right here. A sub 0 is the amount we started with. At the end of 1 year, we have the initial amount plus the amount earned with that interest rate. But then you can see what happens is at the end of the second year, we take this amount, which was calculated and is A sub 1, and we multiply it by 1 plus R, which leads to this formula right here. All right. Well, the value of an investment is an exponential function of time. We call interest computed in this way compound interest, because the interest becomes part of the investment so that the interest earned is on the interest itself. Let's look at the formula for compound interest compounded annually. So if a principal P is invested at a fixed annual interest rate R, which is calculated at the end of the year, then the value of the investment after n years is A equals P times the quantity 1 plus R raised to the n, where R is expressed as a decimal. You've probably seen ads for investments where they say that it's compounded monthly or maybe daily. We can modify this formula for interest compounded instead K times per year instead of just annually. So let's take a look at that formula. Suppose a principal P is invested at an annual interest rate R compounded K times per year for T years. Then R divided by K is the interest rate, which is compounded each period, and K times T is the number of compounding periods. Then the amount in the account after T years is given by A equals P, the principal amount, times the quantity 1 plus R divided by K, all of that raised to the KT. Let's work an example where we use this particular formula, and the example is find the amount of an investment that's accumulated after investing a principal of $1,500 for 5 years at an interest rate of 7% compounded 4 times per year. All right, so what we need to do is the important information, of course, is the 1,500. It's 5 years, 7% is the interest rate, compounded 4 times per year. So that's the information we need, and we would plug it into this formula that we just looked at. So let's do that now. We're looking for A, and we know that P was the initial amount of $1,500, and then we would have 1 plus the interest rate, which is R, which is 0.07 as a decimal. We need to divide that by the number of times that it is compounded, which was 4 times per year. And then that's all going to be raised to the number of times that it's compounded per year times the number of years, which was 5. All right, obviously you would plug all of that into a calculator and have the calculator actually create that calculation for you. And if you would do that, you would find that the amount of money is actually equal to $2,122.17. So you've accumulated a fair amount of money in just that 5-year period. Let's turn this around a little bit and do an example where we have to find the time it takes for a certain investment to occur. Judy has $500 to invest at 9% annual interest compounded monthly. How long will it take for her investment to grow to $3,000? Once again, the important information that we need to carry over with us is, starts at 500, the interest rate is 9. We want to know how long it will take to reach a value of $3,000. So once again, that's the same formula, but we have different information to plug in. All righty, so we know that we're looking to see how long it takes to end up with $3,000. We're starting off with 500. 1 plus the interest rate of 9%, so that's 0.09 over 12 because it's compounded monthly, so 12 times a year. And again, 12 times t, which is the variable, and we're looking for how long it will take, how many years it will take to accumulate to 3,000. This problem is really easier to solve using the grapher, because what we would do is plug in y equals 3,000, second equation y equals that formula, and when we do that, let me show you the result. We get this graph that shows the point of intersection is right here, and specifically we get 19.98, we'll round that off, for x, which is really the t in our formula. And of course, the y equals 3,000 was the final amount that we were looking for. Therefore, what we're going to say is that it would take just slightly under 20 years, or in other words, 19.98. And so call it 20 years, and that's how long it would take for her to get $3,000. Now, you could have solved that problem using logarithms, and I'll leave that to you to do on your own to show that you would get the same answer. What I'd like to do now is try an example in which we have to find the interest rate. So let's take a look. Stephen has $500 to invest. What annual interest rate, compounded quarterly, 4 times a year, is required to double his money in 10 years? The important pieces of information here are he starts with 500. The interest rate is what our unknown is. We know it's compounded 4 times per year, and we want to double his money, which means that we're looking for $1,000, and the length of time is 10 years. Okay, so that's the information we need to carry over, and what it would look like is this. We want to know how long it's going to take, or we know how long it's going to take. We want $1,000 with an initial investment of 500. We know that it's 1 plus the interest rate, which in this case is what we're looking to solve. Compounded quarterly means divided by 4, and then we raise that to the number of times it's compounded times the number of years. So this is the equation we have for finding out the interest rate for it to double within 10 years. Once again, let's use the grapher to solve this. So let me show you that graph right here. We have the intersection occurring right here, which is when x is equal to 0.06991877. Well, of course, basically what that's telling us, if we round it off, is that we would have 0.07, or you could even say that it's 0.0699. So the interest rate R would be 6.99%. Okay. Well, let's take a look at a formula that we have for compounding interest continuously. And that formula looks like this. Suppose a principal P is invested at a fixed annual interest rate R compounded continuously. The value of the investment after T years is A equals P times E raised to the RT. Let's take a look at an example where we're going to use this formula for compounding interest continuously. And the example is, suppose we invest $1,250 at 5 4/10% interest rate, and it's compounded continuously. Find the value of the investment at the end of 6 years. So the important information to cull from here is the initial investment of $1,250, the interest rate of 5 4/10%, and the length, which is 6 years. We'll take that information and we'll plug it into the formula for compound interest continuously, which is right here. And so therefore we have A equals 1,250 times E raised to the R, the interest rate, 0.054, and that's times 6, the number of years. Once again, you could either do that graphically, but this time it's fairly easy to plug directly into the calculator, and that's going to yield an amount of money which is $1,728.31. Well, now we're going to turn our attention to what's called present value and future value of an annuity. An annuity is a sequence of equal period payments. The net amount of the money put into an annuity is called the present value. The total value of the investment returned from an annuity consists of all the periodic payments that you've made together with all of the interest. And this value is called the future value. Let's look at both of these formulas. We'll start with present value. The present value, PV, of an annuity consisting of n equal payments of an amount R, dollars, earning an interest rate of I per period, which is the payment interval, is given by PV, the present value, equals R, the payment you make each period, R times the quantity, 1 minus, in parentheses, 1 plus I raised to the negative n, and that divided by R. What about the future value? The future value of an annuity. The future value, which we label as FV, of an annuity consisting of n equal periodic payments of R dollars at an interest rate I per compounding period, that's the payment interval, is given by FV, future value, equals R times 1 plus I in parentheses raised to the n minus a 1 divided by I. Let's look at an example of a loan. Carlos purchases a new pickup truck for $18,500. What are the monthly payments for a 4-year loan with a $2,000 down payment if the annual interest rate, labeled as APR, is 2.9%? So, important information that we need in this particular problem, we need the fact that that's how much he pays. However, we have to take into account that he is going to put a down payment of $2,000, which means that in terms of the loan, he's only taking a loan for $16,500. The other information, it's a 4-year loan, and the interest rate is 2.9%. So let's plug that into our future present value formula. So we have present value equals the R and all of this here. So what we have is this. 16,500 is the present value. That's how much of the loan is. So 16,500. Now, what we're calculating is how much is his payment going to be. So we don't know R. Times 1 minus 1 plus I, and I is the interest rate, so 2.9, which is 0.029 as a decimal, over 12, the number of times that, or the number of periods, which is each month, raised to the minus, and n is equal to the number of years times the number of payments per year, so times 12, and that's all over I, which we already said is 0.029 over 12. Now, of course, what we want to do here is solve for R. And that would involve basically taking 16,500 and dividing it by that arithmetic expression. If we were to do that, we would find that R is equal to $364, and if I round it off, 48 cents. Actually, I rounded off, it's 4.7, so if I round it off, it would be $364.49. So that would be the payment that he would have to make each month. However, because of that rounding off, he would make a slightly less payment as his last payment to account for that. Well, now it's time for you to try a problem, and I'm going to give you one that involves a loan. Carla purchases a new pickup truck for $18,000. What are the monthly payments for a 6-year loan with no money down if the annual interest rate is 5 4/10%? Pause the video while you work in this problem, and when you are finished, restart the video to check your solution. Welcome back. Let's find out how you did on this problem. We know that she's going to take a loan for the full amount, $18,000. It's for 6 years, and the interest rate is 5 4/10%. And we're interested in finding out how much her monthly payment would be. All right, so let's take and plug this into the formula. We have 18,000 is equal to R, which of course is what we're going to calculate, and then 1 minus parentheses, 1 plus I, and I this time is 0.054 over 12. She pays each month. That's going to be raised to the negative 6 times 12, because it's 6 years, 12 payments per year, and that's all over I, which we already have said is 0.054 divided by 12. Once again, it would be 18,000 divided by this, which would give us a value for R, which is then the monthly payment that Carla would have to make, which R is going to be equal to $293.24. All right, well, I hope that's the answer that you got when you worked out that problem. In this lesson, we explored the mathematics of finance. Be sure to work the exercises that your teacher assigns, and we'll see you next time.